Hello, I want to welcome you to this tutorial demonstrating the Apogee toolset, and more specifically we'll be focusing on multi-objective optimization and a demonstration of how to use this technique within the Apogee tools. The problem that we've discussed in the prior tutorials has been related to the manufacturing of a cylinder that would be a component of a fluid reservoir, and specifically we have identified nominal parameter dimensions through the design process, and associated tolerances would be assigned to each one of these. Now the objective is that with these tolerances and with these nominal values that we would be able to satisfy given requirements or specifications for the inside volume and the cylinder mass. So we've developed our models that will allow us to compute the response results as a function of the parameters, and then also we've recognized that there are variation properties that we need to deal with for each one of these parameters also, and we need to try to determine what would be the probability that we would be compliant or non-compliant with respect to our specifications on the indicated responses. So in our prior tutorials we took this problem and we set it up and we performed a sensitivity analysis. We also performed a Monte Carlo analysis to confirm these results, and basically what we found is that with the current design that the cylinder mass would be non-compliant. Our PNC for the cylinder mass would be approximately 22%, and our PNC for the inside volume would be approximately 8%. So this design is really non-compliant, maybe marginal at best if you wanted to take it that far, but really it's not going to be a good producible design that we can rely upon. Our objective is for this illustration is to try to achieve both response PNC, cylinder mass and inside volume, that would be less than 1%. We approached this problem before with trying to just reassign tolerances to the four primary parameters, allocate those tolerances with the objective of meeting our 1% PNC. When we tried the statistical allocation, we found out that we could marginally get there, but primarily we had to really tighten up the tolerance on the uncertainty of the material density. And with that, by getting its standard deviation down to about 0.07 from the original 0.21 that we had at the beginning, is that we could get the PNC for the cylinder mass down to about 0.6%, less than our 1% objective. However, the end result was that for the inside volume, we were still basically about a 8% PNC on it. We could tighten our tolerances and get down to 1% or less, but it did drive a lot of the tolerances in other areas, and then we still had this problem of meeting both requirement PNCs at the same time. So basically we need to step back and relook at this design, and we need to consider what would be the selection of new nominal values and new tolerances that would allow us to meet our stated performance objectives. So what we're going to do is, in reviewing this design, is to step back and look at it and say, well, what would be the possible feasible values, minimums and maximums, for each of our four parameters: height, outside diameter, wall thickness, material density. So what we determined is that we could really accommodate any height from 25 to 35 centimeters, and we could also support process tolerances from 0.03 to 0.2 on this particular parameter. For the outside diameter, we could pick any value within a range of 10 to 15 with process tolerances from 0.01 to 0.1, and the wall thickness could be from 0.15 to 0.35 with wall thickness tolerances from 0.005 and 0.05. And then the material density, we really want to use a particular material that has a density of 2.7 grams per cubic centimeter. But what we can do is work with the uncertainty properties of that density, and they could be anywhere from the standard deviation could be from anywhere from 0.1 to 0.5 grams per cubic centimeters. So basically we have a design space for different conditions, nominals and uncertainties, for each one of our parameters, and our objective is to find the value within each one of these design spaces, each one of these regions, that will satisfy our particular constraints for our performance objectives. So our constraints that we want to satisfy at the conclusion of this design is that our inside volume PNC and cylinder mass PNCs would be less than our 1% or 0.01 objectives. But also we need to keep the outside volume less than 5,500 cubic centimeters, the material volume greater than 250 cubic centimeters, and we have goals that we would like to satisfy where the PNCs for our primary objectives, we would like to get those to 6 sigma level of quality of 3.4 times e to the minus 6. So these are our objectives. We have design spaces, we have constraints and goals, and we can now go formulate a multi-objective optimization problem to try to find a design that would be compliant with these conditions. So let's go to the worksheet that we've had before, and we've made some modifications to this since the last session. The primary formulas and conditions are the same, but we've added more information to it. So we have our 4 primary parameters identified, and for these parameters we have defined them as noise parameters with given means and standard deviations that are associated with the stated tolerances. So we have each one of these defined that we'll be working with in this particular problem. Okay. Now then, we've also defined our inside volume and our cylinder mass specifications, and then we've also defined additional responses that would be related to our constraints that we need to satisfy in this design. So just to see what our starting point is and see that we do have the original values that we stated and the original tolerances and uncertainties that we stated for this design, let's go perform a sensitivity analysis and confirm that we do have the non-compliances that we stated in our definition of the problem. So I'll run a sensitivity analysis on the inside volume and the cylinder mass, and I'll run each one of these. And sure enough, we see that we're starting with a design that has a cylinder mass PNC of about 22% and an inside volume probability of non-compliance of about 8%. Okay. Now then, let's go back to our problem and let's look at how we can define our design space for each one of these parameters. So for the height parameter, let's go look at its X definition, and where we had defined this as a noise parameter before, let's define this as a continuous parameter. And for a continuous parameter, what it says is you can pick any feasible value between a minimum and maximum range, and in this case I've indicated our minimum of 25, our maximum of 35, and when I pick any value within this range, it will have some uncertainty that's based on our manufacturing processes, and the uncertainty that we're going to be evaluating is actually located in cell I5. So basically cell I5, the standard deviation, is computed as a result of the assigned tolerances. For the outside diameter, let's go set this as a continuous parameter with minimums from 10, a maximum of 15, and with a standard deviation that's in cell I6. So one thing you will notice that for this setup, I have included cell references to define conditions rather than just putting in nominal values in each one of these fields. For the wall thickness, we will make this a continuous parameter with a thickness minimum of 0.15 up to a maximum of 0.35 with its uncertainty in cell I7. And then the material densities will be a mean of 2.5667, which was the mean of our triangular distribution we had before, and the standard deviation of 0.21 that we've identified. Okay. So actually we are going to leave this as a noise parameter, but one thing you will recognize is that the mean is coming from cell I8 and the standard deviation is coming from this cell within our spreadsheet. Okay, now then, what we want to do also when we go examine this design space, in addition to looking at nominal values for the parameters, we want to examine ranges, potential ranges for each one of the tolerances also. So let's go take this cell F5, which is the tolerance for our height parameter, and what we have is we have defined it as a X, which would be a continuous parameter, which says that any tolerance for the height from 0.03 to 0.2 would be acceptable with no variation on the tolerance itself. Then we have done the same thing for the outside diameter, made it a continuous parameter with any tolerance from 0.01 to 0.1. The wall thickness has a feasible range from 0.005 to 0.05. And then our final X parameter will be the standard deviation for the material itself, about the mean of 2.5667. And in this case, a minimum of 0.1 up to a maximum of 0.5 would be acceptable standard deviation range for this particular parameter. Okay, so we've defined our X's, and we'll go look at these in the formulation editor. And we see the name for each one of these X's, the type of parameter it is, standard deviations that have been assigned, and the feasible values that have been assigned for these also. For the responses, remember that in the prior tutorials we had the inside volume and the cylinder mass defined. Now we've defined additional responses for the outside volume and the surface material volume. And I'll discuss why identifying these as additional responses in a few moments. Now then, to do an optimization problem, we had constraints against our particular objectives that we're looking for. So as we're examining the design space to find designs that could be compliant, each design, any design we pick, has to be compliant with certain constraints. Those constraints are that the inside volume PNC and the cylinder mass PNC should be less than 0.01. So notice that in the constraint we're evaluating not just the nominal value but the PNC for that result. We had a constraint for the outside volume that it should be less than 5,500. In the material volume, its mean value should be greater than 250. Okay. In addition, we've defined goals where the inside volume PNC, we would like its PNC to be less than 3.4 e to the minus 6, our 6 sigma objective, and the cylinder mass would also like to have its PNC less than 3.4 e to the 6th. So this is the complete formulation, and now I'll go show you how I establish the constraints and goals that you see defined in this formulation editor. To define a constraint in the Apogee Tools, you would go to this triangular bounded region icon for defining constraints. And what you can do is then define any name that you want to define for the constraint. You define this. But a constraint would be associated with a computed response of our design. So you can pick which response that you want to use here. And I'll just pick the inside volume for this particular one. And then when you evaluate the response, we have the ability of evaluating either the mean, the standard deviation, or the PNC. And in this case, we're trying to satisfy a PNC objective for inside volume. You can select the operator with respect to that aspect, or this PNC. In our case, we want it to be less than or equal to 0.01. So this is the way that you would define a constraint within Apogee. And I'll cancel this since I've already defined these. To define a goal, you would go to the yellow star, the define the goal icon, click on it. You can also define any name for this goal. Select the response from which this goal can be computed, and I'll do the outside volume for this one, this example. You can also select the mean, the standard deviation, or PNC. And for the outside volume, we were evaluating well, actually we did not. We didn't have a goal here on this. Let me go back and change this to what we did have. Let's use the cylinder mass. Okay. And in this case for the mass, we had the P&C was a goal that we wanted to be less than or equal to 3.4 e to the minus 6th in this case. And then for goals, since you can have multiple goals and there's a chance that all goals cannot be satisfied simultaneously, you can establish priority levels in order to determine which goals will be worked more aggressively than others. So a priority level of 1 would be the highest priority, with priority level 3 being the lowest priority for any goals. And then you can assign weights to these also. So this is the way goals would be defined within the Apogee toolset. Okay, now that we've defined our formulation, we can go set this up to go run it, and the options will let us establish conditions for your multi-objective optimization. The concept we're using within the Apogee toolset for optimization is a genetic algorithm approach. And in this approach, you will define a number of generations of solutions that will be created. And within each generation, which you can visualize as being a family of generations, we will have 100 members is what we've defined. And you can change these conditions if you desire to do so. And what we will do is then generate this number of generations with 100 solutions in each potential generation, evaluate all these, rank order each generation, identify the solutions that are most compliant, identify the ones that are non-compliant. We'll draw a cut line, reject the lower level solutions, the lesser compliant solutions, and then we'll repeat this process over and over, generating new solutions for each generation. And we're going to use a criteria to stop is that at any time that we have gone through 20 generations without any improvement in our results, our responses, our constraints and goals, then that's the point at which we will terminate and stop the optimization run and return then the best solution that's been achieved at that point in time. As part of running optimization, we'll also be running sensitivity analysis on every one of the computed responses. So we're going to set this up to do a first order sensitivity analysis where we're evaluating the response standard deviation, computing the response P&C, and then evaluating those results as part of our formulation. So to run the optimization, we will go to this little running person icon and click it to actually run the optimization. So here we see that the optimization is running, and you can see the current generation that's being evaluated, the members of the generation up to 100 is computed for each one, and then we can evaluate here how we're performing collectively among all of our constraints, all of our goals, different priority levels in this problem. So we had one priority 1 goal, which is the blue line. We had a priority 2 goal, which is the green one, and our constraints are represented by the red line. And what we're looking for is to try to drive each one of these conditions, the goodness, if you will, or the feasibility of meeting these constraints and goals, drive this condition to 0, which would indicate that we satisfied constraints, and any number greater than 0 would indicate that we had not satisfied a constraint or a goal. So in this case, we're going through and evaluate different solutions. You can see the values being loaded in the worksheet as we go, and we're going to run through this problem and keep examining solutions until we have gone 20 generations without any improvement in our basic design. And you can see here the number of solutions that we've created at this, or generations that we've completed at this point in time without any improvement in the solution. So anytime we get a solution, it'll revert back to the first generation, and we'll continue on. So at this point in time, we have run about 30 generations. We've evaluated about 3,000 solutions, and looking at different combinations of values for these each design space, each parameter that could be used to assess this. So I'm going to let this run. We'll just look at the generations of that improvement, and when we get this to a point that it concludes, then we will go and look at the results. Okay, so our optimization has actually gone through 84 generations with 100 solutions per generation. So this is on the order of 8,400 solutions have been evaluated. We have gone the last 20 generations without any improvement in the result. And now we'll acknowledge that the optimization run is completed. We'll create a optimization results workbook and we'll evaluate the results. So what we've obtained and in examining results is for our 4 constraints, 2 on the means, the outside volume and the material volume, and then the 2 on the PNCs for inside volume and cylinder mass, is that we have met all of these constraints. So our outside volume is less than 5,500 cubic centimeters, our material volume is greater than 250 cubic centimeters, and our PNCs are both below 1%. With respect to our goals, we had PNC objectives of getting down to 6 sigma, 3.4 to minus 6. We did not satisfy those, but we did the best we could, and we did get below our constraints, which is the primary thing that we're trying to satisfy. Now the results of the optimization are indicated over here in the other portion of your worksheet, and actually what you have is for each generation, the best solution, the highest ranking solution in each generation, is you have results presented for each one of those in terms of the selected parameter values for nominals and tolerances and standard deviations in our case, and then also for your responses you have the means, standard deviation, and PNC for each of the responses that we've defined and used within this formulation for this optimization problem. The best solution is actually down here in the list in the 84th generation. So this one solution here with these nominal values is what were selected for this particular result. And then for this final 84th generation, all 100 members of this population are then shown down below, so you can go evaluate and see are there any other solutions that may be compliant by evaluating their the response conditions and see if any of these could be usable. But the best solution that based on the information the tool had available to it is what's presented at the top and is what is returned to your Excel worksheet. So let's go back to our Excel worksheet, the original sheet we had, and we see here the new values, which are different than what we started with, are the final values that were selected as the best run out of our various generations in our optimization routine. So now then what I could assume is that if I use these values and reran the sensitivity analysis, that I expect to see PNCs less than 1%. So let's go do this, and let's run the sensitivity analysis one more time, and I'll do this for the inside volume and the cylinder mass, our 2 primary responses we have been evaluating. And what we see for cylinder mass is we do have our 0.008, 0.8% probability of non-compliance. We see that we have a result for the cylinder mass that's very nicely centered within our specification limits. We can evaluate the contribution to variance for each one of these, and still the material density is really what's driving this this condition. For the inside volume, we see that we're not very well centered, so we may want to go back and possibly re-examine this specification, re-examine other conditions for the design. We do have a PNC of about 0.6%, which is certainly compliant with our 1% objective, but we could probably do better if we could center this response up within the specification limit. So maybe different ranges for the parameters, maybe re-examine is the spec even correct that we're working with. So let's give you a chance to evaluate those conditions. So in this problem we have examined this, we've looked at thousands of solutions, evaluated many alternatives, and we did come up with a result that would meet our design constraints, and worked as hard as it could to get to our goals, but we didn't quite make it in this particular problem. So this concludes our tutorial on using the multi-objective optimization technique that's included in the Apogee Tools. Hopefully you've recognized it with basically a progression of going through starting with a standard Excel worksheet, defining conditions for the parameters that will impact the quality of the design, that we are able to evaluate a basic design we're given, we're able to allocate standard deviations or tolerances to the parameters to find improved designs, and then we're also able to use multi-objective optimization to examine design spaces to try to find a compliant solution that will meet our performance objectives. So if you have questions or comments, feel free to send me an email, give me a call. I'll be glad to discuss your applications with you. If you want to try the Apogee Tools, you can go to stat-design.com. You can download the installation file for the SDI Tools. Your initial installation will come with a free 7-day trial, and if you find ways that you can use this tool, then contact us and we'll set you up with either a temporary or perpetual license. So I want to thank you for your attention and attendance at these tutorials, and if you have any questions, please let me know.